All right, I hope you're all doing well. We're going to do one more thing with isotopes. This is a PowerPoint that I put on Canvas a long time ago. I will resubmit this so you can look at this also without the video notes. This slide talks about how scientists came up with a new unit for mass for very, very tiny objects. For example, remember that electrons, protons, and neutrons that are in the atom actually do have a mass. They are particles, but they have a teeny tiny mass. So instead of saying grams, they made up a new unit called the atomic mass unit, which makes sense because we're talking about the particles that are in the atom. So you can see the mass of an electron is really tiny, 0.00549 AMUs. A proton, 1.007, a neutron, 1.008. So you see that these two are very close to the same mass, and in AMUs, they're very close to 1 AMU, which makes it very easy to talk about the mass. For example, if we were going to talk about the mass of a proton in grams, it would be 1.66 times 10 to the negative 24th grams, which is a really teeny amount of grams. So to make things easier, when you're talking about small particles, scientists came up with this new unit, which is equal to a certain amount of grams. If you've noticed when you look at your periodic chart, so if you don't have your periodic chart out yet, pause the video and get your periodic chart out. If you find boron, which is in group 13, so up here I drew a picture of it. You see a 5 up here, which remember is the atomic number, which tells you every single time the amount of protons, and that's what makes boron boron. So it's only going to be a boron element if it has 5 protons. This number down here we have not talked about yet. On your periodic table, on your key for hydrogen, it says atomic weight. I would cross that off. A better term for it is atomic mass. So what exactly is this number down here? Obviously, it's some kind of a mass, but what does it actually represent? When you're dealing with isotopes, and for this example, boron has 2 isotopes, you know that some elements might have 3 isotopes, might have 10, 20, right? Boron only has 2. So it has 2 versions of boron. And one is called boron 10 and one is called boron 11. And remember, this number right here is called the mass number. So we could take this number, the mass number 10, and subtract the atomic number. And remember, we would say that this boron, 10 minus 5, has 5 neutrons. So it has 5 protons, 5 electrons, and 5 neutrons. Boron 11, how it's different is, because its mass number is 11, if we subtract the atomic number minus 5, it has 6 neutrons. And remember, that's what makes these 2 isotopes. They have the same number of protons, they're both boron, 5, but they have a different number of neutrons. So boron 11 has 1 more neutron than boron 10, and that makes it more massive. So it would have 1 more AMU of mass than boron 10. If you were to have a piece of boron, which is a solid, and you had a chunk of it, you're going to have some isotopes that are boron 10. So some of the elements or the atoms would be boron 10 and some would be boron 11. But scientists have found that in nature, right, there's always a certain percentage of these 2 isotopes in a chunk of boron. So they have found that boron 10, you would find about 19.8% of the atoms in that chunk of boron would be the boron 10, which only have 5 neutrons. And they have found that boron 11, which has 6 neutrons, would be about 80% of that sample of boron. And these percentages are always the same no matter where you find a chunk of boron, for example. So because we have different isotopes for the same element, right, you can see that this has something to do with the mass. This is going to be an average of all of the isotopes. And because these 2 do not exist in nature as 50% and 50%, we can't do an average like we usually do. So if we were going to do a normal average, we would take the mass of this one, so that's the mass of the whole isotope or atom, and here's the mass, right, again in that tiny little unit, so it's a teeny tiny amount of grams, of boron 11, we would just take this mass, add it to this mass, and divide by 2. But the problem is that only works if this was 50% and this was 50%. So to figure out the average mass of all the isotopes of boron, you have to do a weighted average. And you've done a weighted average before, probably in math class. So we're going to look at how to do a weighted average. All right, so the first thing you do is you take the exact mass. Again, U is just an abbreviation for AMU. Just like grams, you can abbreviate with a G. You can shorten this to U. So this is the mass of boron 10, and this is the mass, the exact mass of boron 11. And you notice that this number is very close to this because if you have 10 protons plus neutrons and they all have a mass of around 1 AMU, then you can see their mass, their exact mass is going to be very close to 10. This one very close to 11. So how you do a weighted average is you take the mass for that particular isotope and you multiply by its percentage as a decimal. So remember, if you want to change a percentage to a decimal, you divide by 100, which actually just moves the decimal over 2 to the left. So here's the percentage as a decimal, 19.8% that you saw in the last slide. Let's just go back and look at that. So you can see 19.8, we just moved the decimal over twice, which is like dividing by 100, and that gives us our decimal form of that. And then boron 11, right, in nature we find is usually about 80.2%. So again, we just took the 80.2, moved it over twice, and now we have our percentage as a decimal. So you take the mass of that isotope, you multiply by its percentage as a decimal, and you get a number. Do the same thing with the other isotope, multiply it by its percentage as a decimal, and you get these two numbers here, and then all you have to do is add these two up. And if you add those up, you can try it yourself, you should get 10.81 atomic mass units. So this is the weighted average of all of the isotopes for that substance. And if you go back and you look at your periodic chart, you can see down here, that's what is shown. This is the average, the weighted average of all of the isotopes, right, that could make up, for example, a chunk of boron. So let's try another one. Lithium has also 2 isotopes. Again, they don't always have just 2, but I picked out 2 simple ones that only have 2 isotopes. So some lithium, if we had, again, a chunk of lithium metal, some of the atoms would be lithium 6, and some of them would be lithium 7. So again, let's make sure that we understand what lithium 6 means. This 6 is the protons plus the neutrons. All the particles are in the nucleus. And remember this 3 here, the atomic number, is just the number of protons. Right, so that equals 6. They told us that. And the protons, right, equal, and comes from the atomic number 3. So all we have to do is subtract 6 minus 3. So this lithium, right, has 3 neutrons. I'm going to write that up here. And what's different about this one? Well, if we take the mass number 7 minus the atomic number 3, this isotope has 4 neutrons. So of course we can see in the mass here, right, the actual mass of lithium 6 in AMUs is less than the mass of lithium 7 because it has 1 more neutron that has a mass of around 1 AMU. So you can see it's about 1 added 1 greater. So again, if we want to see how they got this number, which is again called the atomic mass, which is the weighted average of all the isotopes, in this case 2, all we have to do is take the exact mass for lithium 6 and multiply by the decimal form of 7.50. And we take the mass of lithium 7, the exact mass, and multiply it by the percentage as a decimal. We add them together, and we should get this number down here. So if they were to put a unit here on the periodic chart, sometimes they do, they would say that the weighted average of all the isotopes is 6.94 AMU, or again, you can abbreviate it with just U. So pause the video and try this one on your own and see if you can get 6.94. hopefully you paused it and you tried it yourself, but we'll do it down here. So I'm going to take the exact mass of lithium 6. So that's 6.015. I'm going to abbreviate it U for AMU. I multiply it by, I'm going to move the decimal. Here's the decimal right here. So I move it 1. If I don't have any other numbers, I have to put a 0 there. So that's going to be 0.0750. So again, this is how I did it. Here was the decimal, 1, 2, or divided by 100. Right, we're going to multiply that out. Let's first do the other lithium. Here's the exact mass, 7.016 AMU, multiplied by the percentage as a decimal, 1, 2. So that's going to be 0.9250. I'm going to actually calculate these. When I multiply these two together, I get 0.45. I would keep a lot of numbers. 25. When I multiply these two together, I get 6.4898. Right, so after I take their exact mass times their percentage as a decimal for each one, then I just need to add these two numbers together. And when I add them together, I'll put it up here, I get 6.940 dot 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 dot. So you can see right here, the average, weighted average of all the isotopes is 6.94. And how you can check it is look at your periodic chart. That's what that number below should be, the weighted average of all the isotopes. All right, I hope this helps. Hope you're all doing well.